In this video, we're going to look at FAA Advisory Circular 25.13091A and how the role it plays in certification of aircraft systems. First, we'll review the learning outcomes for this module. Then we'll look at 25.13091A and how it tells you to comply with 14 Code of Federal Regulations 25.1309. We'll talk about fail-safe design standards and approaches. We're going to come up with the consequences of failure and degrees of those, and then they have associated likelihoods, and we'll have qualitative and quantitative ways of discussing those likelihoods. We'll talk about means of analysis to demonstrate compliance, and then we'll have our usual summary and discussion of what's next. So the learning outcomes for this module, when we get done, you ought to be able to state what's in 14 CFR 25.1301 and 14 CFR 25.1309. We did that the last time. And then this meeting is about explaining how Advisory Circular 25.1309 defines extremely unlikely, unlikely, probable, etc. And next one, we'll talk about how SAE ARP 4754 and 4761 and RTCA DO 178C and DO 274 figure into aircraft certification. So previously we looked at Code of Federal Regulations 25.1301, which talks about the function and installation of aircraft systems. And a pithy way of putting this is a system's got to do what it says it's going to do. And we also looked at 25.1309, which has general requirements, which basically says the more likely something is to happen, the less impact it should have on the crew of the aircraft. Requirements having monitoring and warnings and giving the crew the ability to respond to failures, and then also demonstrating compliance by analysis. So, but it doesn't go into the details. So how do you actually demonstrate compliance with these regulations? Well, advisory circulars are exactly what it says. They're circulars that are made by the FAA that give advice. In some cases, it's manufacturers. It says here manufacturers, but it can also be to pilots, to airlines, etc. But in this case, we're talking about advice to the manufacturers on how to demonstrate compliance with regulations. And so there's Advisory Circular 25.1309. It's edition 1A, which tells you how to comply with the 14 CFR 25.1309. And it talks about the consequences, and it's going to break them into several levels of consequence. And there, like I mentioned earlier, there's going to be qualitative and quantitative definitions of likelihood. And then there'll be means of compliance. So different kinds of analyses you can do on your system to demonstrate compliance. So one of the keys in 25.1309.1a, AC 25.1309.1a, is this language about fail-safe design standards. In any system or subsystem, the failure of any single element, component, or connection during one flight should be assumed regardless of its probability. Such single failure should not prevent continued safe flight and landing or significantly reduce the capability of the airplane or ability of the crew to cope with resulting failure conditions. Subsequent failures during the same flight, whether detected or latent, and combinations thereof should also be assumed unless their joint probability with the first failure is shown to be extremely improbable. So again, this is not failure is not an option. This is failure is presumed, and you need to design around it. That's really what we're talking about here. So here's some approaches to fail-safe design. The whole idea is you want to design for integrity and quality to start with. So you want your system to have as resilient a design as possible. You should have redundant or backup systems so you can have continued functioning after multiple failures. Systems should be isolated from each other so that one failure doesn't cause another. You should be able to demonstrate reliability. When things go wrong, you should detect that and advise the crew. There should be specified flight crew procedures for when things do go wrong, what you do. You should be able to check on the condition of something. If it's not giving you a warning, you still should be able to find out whether it's working properly or not. You should have design failure effects limits. This is like the crumple zone on your car, your crash. So it's designed to sustain damages and limit the impact of failure. And then you should be able to control the failure path so that when things go wrong, if it does have consequences on other systems, you can direct that and control that. And then finally, there's margins of factors of safety. So that when you do design, say structural design, you're specified to give it, additional. You think it only needs to have such a certain measurable strength, and so you have a factor, say 1.5 above that, to guarantee that if something goes wrong, maybe just some error in the manufacturing, it's still going to work. Finally, there's sorry, I said that was the last one, but the not error tolerance. Just being able to tolerate errors again through it. So maybe make corrections, decide on the right values and the like. So if you have multiple systems with one of them is erroneous, you can throw out the erroneous system reading and the like. So we're going to define 3 different levels of the consequences of failures, and they're going to have associated likelihoods with them. Minor consequences are those that really don't really change the safety. It's just, a light bulb goes out, but it's an inconsequential failure or something like that. And it doesn't really require any extra crew capabilities. And again, we're going to presume these are probable. And so probable here, in the qualitative definition of probable here, is they're anticipated to occur 1 or more times during the entire operational life of each airplane. So it could happen once, again, in the life of an airplane. Quantitatively, that's a probability of greater than 1 times 10 to the minus 5th per flight hour, or once every 100,000 flight hours. So we assume it's going to happen more than once every 100,000 flight hours. That's what a minor consequences, which we assume are going to happen. That's a probable happening. Major consequences, though, reduce the capability of the airplane or ability of the crew to cope with adverse operating conditions. So safety margins can be reduced, your functional capabilities can be reduced, and it's going to have an impact on the crew workload. So they can be 2 degrees, significant and severe. All right, so these are failure events that have a major impact on the operations of the aircraft. They could be threatening, but not life-threatening, but not not all the way there. So major consequences have to be improbable, and the qualitative definition of improbable by the FAA in AC 251309 is not anticipated to occur during the entire operational life of a single random airplane. However, they may occur occasionally during the entire operational life of all airplanes of one type. So again, you don't expect it to happen over the life of the airplane, but it can happen during the life of the fleet. And so this quantitatively is the probability is greater than 10 to the minus 9, but less than 10 to the minus 5. Finally, a catastrophic failure is a failure that prevents continued safe flight and landing. So if you don't have continued safe flight and landing, you have unsafe flight and landing. So I mean, this is a loss of aircraft and loss of people. That is what the FAA refers to as souls on board, SOBs. It's kind of a sick joke with the FAA. And catastrophic consequences have to be extremely improbable, and the qualitative definition of extremely improbable is so unlikely that they're not anticipated to occur during the entire operational life of airplanes of one type. So it's, I mean, you maybe one instance over the fleet of the airplane is sort of what's anticipated, although desirable that it doesn't happen over the entire fleet, life of the fleet. And quantitatively, that's a probability of less than 10 to the minus 9 per flight hour, which is once per billion hours. So these sort of define an inverse relationship on likelihood and consequence. If you look on the horizontal axis here, we have probability of the failure condition. And this is sort of backwards. This is going from more likely on the left to less likely on the right. Whereas you have the consequences on the vertical axis, and these are increasing in order of from bottom to top, in order of increasing negativeness. So from normal at the bottom to a catastrophic accident. And there's a trade-off between probability and consequence, and that's the definition of risk. So sort of constant risk, it can either be highly probable but of little impact, or of extremely unlikely but of substantial impact. So this is there's sort of a trade-off here between a consequence and probability. So AC 251309 gives you guidance about how to demonstrate that the system can tolerate failures, as it says. So regardless of its type, an analysis should show that the system and its installation can tolerate failures to the extent that major failure conditions are improbable and catastrophic failure conditions are extremely improbable. And so there's several different ways of doing this, and 251309 just mentions several. And one is the functional hazard analysis, which is where you go through the different systems and subsystems and components, and you identify potential hazards, and you describe the function and its operation and the impact there. So if you have a system that you can demonstrate that the minor failure conditions for a system, as long as you can show that that's isolated from other systems, you're good enough. If you have major failure conditions, you have to show that it's improbable. And you have to show that the more severe ones are lower likelihood than the less severe ones. The major failure condition analysis can be done with not only, this comes after the functional hazard analysis, but what's called a FAMEA, failure modes and effects analysis. So this is where you look at when it fails and then what's the percolating down the path impact of that failure. There's also a fault tree analysis, which is sort of like a logic diagram where you say, okay, this failure happens when this or this or this and that. And this is described with logic diagrams. And then you can demonstrate that you have redundant systems that are isolated from each other. And so if one of them fails, the other one doesn't. For catastrophic failures, you have to show they're extremely improbable and use the same tools that you do for a major failure condition analysis. So that's what's in Advisory Circular 1309. So advisory circulars are advice from the FAA. 251309-1A shows how to comply with 14 CFR 251309. It gives us a mean to achieve fail-safe design. We get the definition of minor, major, and catastrophic consequences, and we get qualitative and quantitative probabilities for those consequence levels. And then it gives us a list of some acceptable analyses to do that. In the next video, we're going to talk about additional advisory circulars since 251309-1A, which enable us to do a design assurance, and that's going to come from SAE ARP 4754, Aviation Recommended Practice, or Aerospace Recommended Practice. And then that's going to reference ARP 4761 for the safety assessment part. And then there's going to be advisory circulars about using RTCA, document 178C for software, and 254 for complex electronic hardware, and 297 for what's called integrated modular avionics.